Welcome to this lecture on modular multilevel converters. So, we have earlier seen the cascaded edge bridge converter as the first multilevel converter. We studied that, and now we are going to study the modular multilevel converters. In short, this converter is called MMC, modular multilevel converter. So, this right hand side picture is the circuit representation of MMC, okay. And like the cascaded edge bridge converter also, we can see that this converter has many cells which are connected in cascade or in series. So, here you can see that for example, cell 1, cell 2, cell 3 up to cell n, these are all connected in series. Okay. So, the principle of this series connection of low voltage cells in order to produce a high voltage is also applicable for the MMC. Okay. We will see this topology in details, but let us first see that the history of this converter. It was first proposed by Professor Marquardt in Germany in 2001 or around 2001, and thereafter the kind of like the converter immediately was not so popular, and there were hardly any publication or any research articles on this converter. However, one company, it was in the process of, they saw the potential of the converter and they started plans to commercialize it. And around 2008, 7, 8, during this time, based on this converter, the first high voltage DC transmission was commercially launched. And when it was launched, then there was a lot of enthusiasm and there was a lot of activity on this converter. And then people started realizing that okay, there is a lot of potential and benefit of this particular MMC, a modular multilevel converter. And after that, within a span of 7, 8 years or 9 years, there has been a lot of work which has taken place on this converter. And if we search, for example, in some online say IEEE database, we find thousands of articles on MMC or its derivatives, and it is not only confined to high voltage DC applications, but it is also used or it is proposed to be used in other grid connected applications, for example, integrating PV or battery systems, or it can be used also for motor drive applications and so on. So, this converter, once we study, we will understand that it has immense potential for many applications in power electronics. Now, before we go into the MMC, let us first understand that the drawback of the cascaded edge bridge converter. As we had studied earlier, we found out that cascaded edge bridge converter is a kind of like quite it has many advantages, it has very unique features. For example, using low voltage devices, we can connect many of these low voltage devices in series or in cascade, and then we can reach a very high voltage. And by using proper PWM techniques, we can achieve a quite a nice sinusoidal waveform at the output. And also there was a fault tolerant feature. I mean, you can bypass one of the faulty cells and can still run the converter. Although the cascaded edge bridge has these advantageous features, but there is a big drawback or there is a big challenge, and the challenge is that the cascaded edge bridge converter requires many isolated sources. The DC bus of each edge bridge is isolated from the DC bus of the other edge bridge. So, we had seen that we make a several transformer secondaries, we use several transformer secondaries in order to make this isolated DC bus of cascaded edge bridge converter. So, there was a need to remove the requirement of this isolated DC sources, and here comes the MMC. Okay. So, MMC does not require any isolated DC source or these transformer fed DC sources. It has only capacitors in the DC bus. Okay. At the same time, it retains the advantages of modularity and scalability, which means that many cells, there are many identical cells in MMC like in CHB, and all these identical cells are low voltage rating, and there are many of them are cascaded and they can produce a very high voltage. So, the advantage of CHB is retained in MMC, but at the same time the requirement of this isolated DC sources, that requirement is removed. So, MMC has only capacitors in the DC bus, and the cell structure of the MMC consists of either half bridge or full bridge. Okay. Like the CHB also, it has a bypass switch. So, if one of the cells is faulty, it is possible to bypass the faulty cell and can still run the converter without shutting down the entire converter. You can bypass the faulty cell, that is the faulty half bridge or full bridge cell, you can bypass it and can still continue to run with it. So, the fault tolerant feature is also present in the MMC like in CHB. So, it is commercially implemented for HVDC, motor drives, STATCOM or other types of FACTS application. And as I told you, many researchers and people in the industry say that it has potential for many more applications in future. Now, in cascaded edge bridge, we have seen cells being connected. Now, when we talk about HVDC application for which MMC is very suitable, we are now talking about hundreds of cells connected in series. Okay. So, in HVDC application, for example, at plus minus 400 kilovolt and say 800 megawatt of HVDC application, we can connect hundreds of cells in cascade in an MMC converter. So, we can now see that this arrangement of series connection of cells is not limited to just a few cells connected in series. We can have hundreds of cells connected in series, and so the concept of modularity, scalability is very much applicable for the MMC application. So, let us now see what is the converter structure, and before we go into the converter structure, we first see the cell. So, MMC, the basic structure of MMC is made up of cells. Okay. There can be hundreds of cells working together. So, what is there inside one cell? Inside one cell, you can see here, the cell can be two varieties of cell. Usually there can be two varieties of cell. One is this half bridge submodule another one is full bridge submodule. Cells are also called submodules, they are interchangeably used. So, you can say half bridge submodule or you can say half bridge cell. So, this is one cell structure, one possible variety of variant of the cell structure. So, this is half bridge and this is full bridge. Okay. This is the full bridge cell. Now, so in case of a half bridge cell, we see that there are two IGBTs like this, which of course are complementary in nature, otherwise it will short the DC bus, and there is this DC bus is formed of capacitor. So, there is only one capacitor here. Okay. So, there is no isolated DC source which is connected to the DC bus of this cell. In a similar fashion, for the full bridge submodule, we have a capacitor here and there are 4 such switches. In the half bridge submodule, this point A and O are the 2 ports of the cell. Similarly, in the full bridge variant, A and B, these 2 are the 2 ports of the cell, okay, or 2 terminals of the cell. Now, if we see this half bridge module submodule, we can see that if we turn on S1, the output voltage is, that is VAO. If we see the terminal voltage as VAO, or this is called the output voltage VAO. If I turn on switch S1, then VAO is equal to Vc. If I turn on S2, then VAO is equal to 0, and this is shown here in this waveform, that VAO, if I turn on S1, then I get VAO as Vc, that is the capacitor voltage is obtained at the output VAO when I turn on S1, and of course, if I turn on S2, then I do not get any voltage. On the other hand, for the full bridge submodule, if I turn on these 2 diagonal switches S1 and S4, then the voltage VAB is equal to the DC bus voltage, positive DC bus voltage, that is plus Vc. On the other hand, if I turn on these 2 diagonal switches here, then I can get a negative Vc, minus Vc voltage on the output, and if I turn on the S1 and S3, or if I turn on S2 and S4, then I get 0 voltage at the output. So, this MMC, the cell can, if we use half bridge cells, then we get 2 levels of voltage, that is 0 and Vc, whereas if we use the full bridge cells, full bridge variety, then we can get 3 levels of voltages at the output, plus Vc, 0 or minus Vc. Now, each cell, what is shown here, also has a bypass mechanism. It is not shown here right now, we will discuss this bypass mechanism sometime later. What is the bypass mechanism? The bypass mechanism is like, there is a bypass switch like this, which will be activated when we want to bypass the cell. If there is, for example, a very severe fault inside the cell and it is no longer usable, then we can bypass that cell and without shutting down the whole converter. This bypass mechanism is not shown here, but we will discuss it sometime later. Okay. Now, so this half bridge and full bridge submodules are present in half bridge, either half bridge or full bridge variety can be used. So, inside this inside this cell 1 or cell 2 or cell 3, inside these cells either the half bridge or the full bridge is used. Okay. When do we use half bridge and when do we use full bridge? We will understand it a few slides later. But let us take the simpler case, let us take the half bridge. So, if we take the half bridge variety, so each cell like this is made up of half bridges. Okay. So, many of these cells, so there are n number of cells and the total n number of cells, that number n can be more than 100. For example, for high voltage DC transmission, say in the plus minus, as I told you, plus minus 400 kilovolt, the number n can be more than 100. Okay. If we look at the structure of this converter now, we see that these n number of cells are connected in series and 6 such. So, this is called one arm of the converter, where suppose we take the half bridge variant. So, n number of half bridge cells are connected together to form one arm of the converter. Similarly, we have an upper arm and we have a lower arm for any phase. So, suppose we have the AC side here. So, this is A phase, this is B phase and this is C phase. Say for example, this is A phase, this is B phase and this is C phase. So, the AC is AC A phase, B phase, C phase is connected like this, and so in each phase we have an upper arm and we have a lower arm, okay, and in each arm we have n number of half bridges. So, B phase is like this and C phase is like this, and here we get the DC. Okay. For example, this converter, if I think of an HVDC application, then this side becomes HVDC here, this is the plus and this is the minus of the HVDC, and then this is the AC grid here. Okay. This is the AC side, A phase, B phase, C phase, and the converter is connected in this fashion with 6 arms. Okay. A phase, B phase, C phase with 6 such arms, and each phase has 2 arms, upper arm and lower arm. Now, there is also something which is called the arm inductance present here. Here you can see there are 6 arm inductors corresponding to each arm of the converter. The arm inductor has a lot of functions. It can control the circulating current inside the arms, and it can also limit the short circuit current in the event of a short circuit on the DC side. We will talk about the arm inductors little bit later. Okay. So, if I now see the features of this converter, we can see that the converter has many modular identical cells. So, each of this cell is a half bridge, which is one of the most simplest structure in power electronics, and each cell has a DC bus which is made up of a capacitor. So, there is no need for any isolation. So, each cell has its own capacitor, it has 2 switches and it has a bypass feature which is not shown actually in this particular diagram. We have not shown the bypass feature, but the bypass feature is present here. Okay. Now, attractive feature of MMC is that we can have low voltage, for example, low voltage transistors or low voltage IGBTs, they can be used in each cell. So, as I said that if the DC side here is plus minus 400 kilovolt, then we may use many low voltage IGBTs inside these cells. For example, 3.3 kilovolt or 2.5 kilovolt IGBTs but many of them inside each cell, say this cell has 2 IGBTs. So, and each IGBT can be rated for say 3.3 kilovolt. Okay. But since many of these cells are connected in series, therefore, we can get to a very high voltage. Okay. And the other feature of this is the fault tolerant operation, where the faulty cell can be bypassed. And also we see one of the attractive features of this converter is the easy scalability of voltage and current, which means that say if I want to have a higher voltage, we can connect more number of cells in series, okay, so as to get a higher voltage. For example, we have a plus minus 400 kilovolt application and then we use certain n number of cells. But if in another application, if we have plus minus 200 kilovolt requirement, then we can reduce the number of cells. Another unique feature of this converter is that it can be used as a DC to AC or an AC to DC application. So, for example, as you can see here in this circuit diagram, you can see that if this is the grid available to me, then with the help of this converter I can VDC side here. Okay. So, then the power will flow from the grid into the HVDC line. From the AC side, suppose we want to send power from the AC grid over a long distance via high voltage DC transmission, we want to send the power to another grid. So, then the power flow is happening from this AC grid here, okay, through the HVDC line. On the receiving end, this is the sending end topology. On the receiving end, we get the HVDC. So, this is the sending end. So, this is the sending end. But on the receiving end, we have the DC voltage available, from which we would like to get back the AC. And so, the same converter. So, on the receiving side, we have the HVDC available to us, and we can use the same converter to connect it to the existing grid on the receiving side, and then the power will be flowing from here to here. Okay. But you see, the same converter can be used. So, we can send power from the AC side to DC side, say at the sending end, and an identical converter can be used at the receiving end. So, this is the receiving end, the identical converter can be used, which will convert that DC into AC, okay, and the power will flow from the DC to AC. So, this is one of the advantages of this converter. So, just summarizing the advantages of the converter, it has modular and simple converter cell like a half bridge, bypass of faulty cells is possible, easy scalability of voltage is possible, and very high quality of sine wave is produced at the output. This we will see in the next slide how the sine wave is produced. So, if we are making say AC to DC converter or a DC to AC converter, then a very high quality of AC waveform can be used by using these cells with the help of pulse width modulation. The common mode voltage is also very low and very low dV/dt at the output, because now the step size on the voltage waveform is very small, because we are using hundreds of cells. So, the step size, so each cell, I mean the step size on the waveform, AC waveform becomes very small, we will see that. and the presence of arm inductance also helps in limiting the short circuit current. So, this is very advantageous, because suppose we are converting AC to DC, and the DC we know that DC circuit breakers are not easily available. It is very difficult to make a DC circuit breaker. So, the arm inductors actually help in in limiting the rate of rise of current when there is a fault on the DC side, because when there is a fault on the DC side, the current will flow from the AC side and will feed into the DC, faulted DC, and at that point of time the arm inductors help in restricting the rate of rise of the current from the AC side into the DC side. Okay. It has good transient response, the MMC has a good transient response during fault condition also, and so the DC side can also be fed from a multi-pulse rectifier in case we are going for a DC to AC application. For example, for motor drive application, if the DC is available, that DC can be generated from a 12 pulse rectifier, and then there can be several cells and we get an AC output which can be fed to a motor drive application. Okay. Now, although MMC has many advantages which we discussed, there are in fact certain disadvantages. There are too many components. Okay. So, the control is complex, however, the control strategy is repetitive for all cells. Okay. So, same control strategy gets on repeating for all the cells, and of course, the cost is more because now we are using many half bridges. Each half bridge has its own gate driver, has its own protection mechanism and so on, but this cost is something which we must be careful, because whenever we talk about cost, there is of course something like a running cost and something like an initial development cost or initial cost. Now, MMC has a very high initial cost, because the converter, building the converter, testing it and making it working. So, it is a very high initial investment, but at running condition the efficiency of MMC, which is you may be surprised to know, is very close to or even more than 99%, the running efficiency of MMC. So, the running cost or the losses are less in MMC, and so it is advantageous when we talk about the operational reduction of losses. Reliability is less in MMC, definitely, because we have many components, and so with many components the reliability goes down, but availability is more. So, if we have many cells, then the availability, so if we can bypass some of the cells, then availability is more. The other disadvantage of MMC is the amount of capacitance. Although each cell has its own DC bus and it is made up of capacitance, but the magnitude of capacitance required in MMC is much more compared to other topologies. We will see one more topology later, for example, neutral point clamp converter NPC. As compared to NPC, the amount of capacitance required in MMC is 3-4 times or even more. Okay. So, that is one of the drawbacks of MMC. The control is also complicated for vector control drives, okay, where full load current is required at close to 0 speed. This is one of the drawbacks, but there is an active research going on. When the motor is running at 0 speed, how do you control the converter with full torque on the motor, but MMC is quite suitable for drives with fans or pumps which do not require full load torque at startup. Now, we see how we can understand the operation of the converter and how can we analyze, because you see with so many cells connected, it becomes a little bit tricky and difficult to understand, like how all these cells are going to be controlled. Okay. It is a little bit challenging, but fortunately if you understand the operation of the cells and how they are connected in series, it is not a difficult task. Okay. So, let us see how we understand this. So, here on the left we show you that one arm of the converter with n number of cells in half bridge configuration. On the right hand side we show the n cells in an arm of the converter, but they are now connected in full bridge configuration. So, we will analyze both of them together. Okay. So, for example, if we take, let us take the half bridge configuration first, it is easier to understand. So, with one cell, let us with this one cell here, as we told you, the output of the cell can vary between 0 or Vc. 0 means when the lower switch is on. So, then we get 0 voltage at the output, 0 voltage here, and this is the output of one, that is cell 1. So, if the lower switch is conducting, then we get 0, if the upper switch is conducting, then we get a voltage of Vc. So, the output of the first cell can be kind of like written like this, drawn like this. Okay. Similarly, the output of the second cell can be drawn like this, also independent of the first one. So, the output here will change from 0 to Vc and here again 0 to Vc, assuming that all the cells have the same DC bus voltage Vc. Now, when we series connect them, that is when we cascade them, so the two voltages get added up, and so these two voltages get added up, what we get like this 0 Vc and 2 Vc. Okay. This much, this voltage we will get between this point here and this point here. Okay. Between these 2 points we will get a voltage which is going like 0 Vc and 2 Vc. So, similarly, if we have n number of such cells connected in series, then we get a voltage which is something like this here 0 Vc, 2 Vc, 3 Vc going up to n Vc. Okay. So, of course, so therefore, by using these low voltage devices and low voltage cells, we can get to a high peak, the peak voltage in Vc can be quite high if n is very high. Okay. If the n is for example 100, then we can go up to 100 Vc. Okay. That is quite a high voltage which can be obtained between the point A and O, that is the arm voltage can be quite substantial in magnitude when the number of cells is quite large. Okay. Of course, we can also control this voltage by using pulse width modulation here. This is not shown, but by using pulse width modulation it is possible to minutely control or vary the amplitude of the VAO voltage. In fact, with n very large, we can get a nice sine wave from the arm of the converter. Okay. See, very nice and quality of sine wave can be produced, because if n is large, this step size here, this is the step size of each, the size, the height of each step in the waveform, when n is very large, the size becomes very small for a fixed magnitude of the AC voltage. So, if n becomes very large, then the waveform automatically approximates to a sine wave. Okay. So, that means suppose this is the sine wave, we are actually getting very with large value of n, we are actually very close to a perfect sine wave, as you can see here. Okay. A very nice quality of sine wave can be produced if n is very large. Okay. So, this is one of the advantages of the converter. Now, in this particular case, we can see that between A and O, the voltage that can be produced can vary between 0 and n Vc. That means, the voltage produced has both DC and AC component. Okay. There is a DC component here, because the voltage is between 0 and n Vc, there is a DC voltage inside it, and whatever AC we want to produce can also be embedded inside that. So, this is what happens with a half bridge. On the other hand, if we see the full bridge, as we have earlier said, can have full bridge can have 3 levels of voltage, that is 0, each cell can be plus Vc and minus Vc. So, suppose this cell produces this voltage here, this cell here can produce the same voltage independent of the first one. So, it can also produce 0 Vc and minus Vc. Okay. Now, if you add both of them, when you are cascading them, then what you can get? You get something like this, 0 Vc to Vc, and then again minus Vc and minus 2 Vc. Okay. So, therefore, if you have n cells in cascaded fashion, then you can get such a kind of waveform at the arm. Now, this waveform of the arm voltage for a full bridge configuration, which is coming between the point A and O here, this waveform can have 0 DC. Okay. The DC component can be 0. Okay. As you can see from the waveform itself, the full bridge variety or the full bridge variant can have 0 DC and a full AC. So, the AC waveform is embedded here. So, this is the AC waveform embedded here. Okay. The full bridge can produce a DC. It is not that the full bridge cannot produce a DC, it can produce a DC, but that DC magnitude can also be 0. So, the full bridge variety can produce a voltage waveform which is like this, okay, but it can also produce a voltage waveform which is like this, okay, with a DC value which can be positive or negative also. So, it can also produce a voltage like this, okay, depending on the rating of the arm. So, this is a 0 DC, this is a positive DC, and this is a negative DC. Okay. So, the full bridge variety is more flexible in that regard, but this DC is definitely present in case of a half bridge. We cannot avoid the DC in case of a half bridge, but we can avoid the DC in case of a full bridge, or we can have the DC in case of a full bridge variety. So, whatever may be the case, whether we go with a half bridge or full bridge, what we understand is that with many cells connected in series, it is possible for us to approximate the arm voltage as very close to a sine wave, okay, within very large value. Okay. We can see here from the even with like 4 or 5 steps in the waveform that I have shown on this waveform, even with 4 or 5 steps we can see that we are approaching closer and closer to a sine wave. Okay. The sine wave can have a DC component, okay. The sine wave must have a DC component in case of a half bridge, but in case of a full bridge it may have a DC component. Okay. So, with this understanding of the arm voltages, let us analyze the converter. So, what we do here is that suppose we take again the simpler case, we take the half bridge variant. Okay, let us start with the half bridge and see how the MMC circuit can be modeled. Okay. So, you see here this all these cells, as I told you, when all these cells are connected, they are just like the previous we can say that these arm voltages can be assumed to be a controllable voltage source. Okay. Depending on how you place the cells, how you place the waveforms, we are basically generating a controllable voltage sources. So, the arm voltage is a controllable voltage source, and the control algorithm will decide what type of a controllable voltage source we are producing. In fact, we are producing a sinusoidal controllable voltage source from this converter, and so this arm here, this arm is now replaced by this controllable voltage source here. Okay. So, this voltage source is representing the arm voltages. So, there are now you can see there are 6 such controllable voltage sources, which are these are the 6 controllable voltage sources which are working together. Okay. These 6 controllable voltage sources are completely independent of each other. So, this is something which is unique for this converter, like there are 6 controllable voltage sources which can be controlled independent of each other, and of course, we will see how to control them so as to create a AC or DC. Okay. So, on this side we have the AC and we on this side we have the DC. Okay. Now, in case we use a half bridge, this controllable voltage source must have a DC component. As we had seen in the last slide, the controllable voltage source here in case of half bridge will have a DC and an AC component, whereas in case we use a full bridge, we may have the DC component and we may not have, or we may not have the DC component. We can make the DC component 0. So, let us see only the half bridge configuration. So, when we see the half bridge configuration, then we can, so we can these controllable voltage sources, we can now write the Kirchhoff's voltage law and can find out what is the magnitude of this controllable voltage source. Okay. What is its magnitude? How is it related to the AC side and the DC side voltages? How they are related with the controllable voltage source magnitude? So, this is shown by this mathematics here. It is easier to understand if we have a DC and we are trying to convert it into AC. Okay. So, we will start with the DC to AC converter analysis, and later you will see that it is the same analysis when we do from AC to DC side. So, suppose we assume that we have the DC available here and we are trying to produce an AC here, balanced AC. Okay. So, we have the DC, and so this is a DC to AC converter. Okay. So, if this is a DC to AC converter, we have the DC voltage available here, where the total DC bus magnitude is E and O point is the imaginary midpoint of the DC bus. Okay. In some cases, for example, in bipolar HVDC transmission, the O point can be physically accessible also, but for this analysis let us assume that O is an imaginary point here. Now, from this circuit we can write the converter voltage equations. So, I can write it here, say, so if I go Kirchhoff's voltage law, so E by 2 minus V u, so if I put this as the plus here, so E by 2 minus V u minus L di dt is the point's voltage A with respect to point O. Okay. This is what is written here, E by 2 minus V u, that is the upper arm voltage. V u stands for the upper arm controllable voltage source. Okay. V u is the upper arm controllable voltage source. So, E by 2 minus V u minus L di dt is equal to V a o t. Okay. So, for phase A, fine, and let us assume that this V a voltage, AC voltage which we want to produce is given by V m sin omega t. Okay. So, we are talking about a DC to AC converter where the DC is available to us and we are trying to produce a controllable AC at the AC side. So, this is the governing equation here which is written here. So, if I neglect the inductor drop, then I can simplify this equation and write E by 2 minus V u t is equal to V m sin omega t. I just neglect the L di dt drop. Now, this is a fairly good approximation. If we will see some example later where you will see that the inductor size is pretty small and the energy stored in the inductors is under steady state, it is pretty small. So, it is a fair approximation to have this L di dt under steady state to be quite small. Okay. So, neglecting this inductor drop, we can write E by 2 minus V u t is equal to V m sin omega t. Okay. So, then this means that V u t is equal to E by 2 minus V m sin omega t. Okay. So, this is the equation of the upper controllable voltage source. Okay. So, as I said, this is the upper controllable voltage source which is like made up of like this, many cells connected in series, and this is what we had made. The upper controllable voltage source is made like this. So, its mathematical representation is given by this equation here, V u t is equal to E by 2 minus V m sin omega t, right. So, this is the equation of the upper controllable voltage source in phase A. In a similar way, like we have shown for upper arm of phase A, we can also write for the lower arm of phase A, and then we see that minus E by 2 plus V L. So, I should write this plus V L here. So, minus E by 2. So, this is what the equation says, minus E by 2 plus V L minus L di dt is equal to V a o t going from the bottom side, and then it is also equal to V m sin omega t, the A phase voltage. And again, if I neglect the inductor drop here, we can say that V L t, that is the lower controllable voltage source, can be written as E by 2 plus V m sin omega t. Okay. So, this is the expression for the lower controllable voltage source, this is the expression for the upper controllable voltage source. Okay. Now, you should note that the upper controllable voltage source, that is V u and V L, both of them have a DC component and an AC component. Okay. You see here there is a DC component and there is an AC component. Here also there is a DC component and there is an AC component. Okay. So, this is consistent with our previous analysis saying that a half bridge, an arm which is made up of half bridges, that arm will be generating a DC plus an AC, and you can see here it is generating a DC plus an AC. Okay. So, if we, so this is the controllable voltage that can be generated by the upper arm and the lower arm voltages. Now, how can I change the voltage here? How can I change the voltage here? Of course, VU and V so that Vm voltage which is being produced by at the output of the converter has to be changed, because we want to change Vm. Okay. We want to get a variable output from the converter, variable output voltage from the converter. For example, for motor drive application this is very much necessary, and if we are going for say V by F application, both the voltage and the frequency will also change. But anyway, if we want to change the voltage output, then that Vm which we were producing has to be changed. And how do we do that? We say that the converter arm voltages can be written as Vu star, that is the control which is given to this converter voltage is E by 2 1 minus m sin omega t, where m is defined as the modulation index and is given as Vm by E by 2. So, here there was a Vm. So, we have taken Vm as a fraction of E by 2, okay, and are defining a new term modulation index m for the converter, which is Vm by E by 2. Okay. And this is what the upper and similarly the lower one, the lower voltages are will look like. So, the earlier equation was something E by 2 minus Vm sin omega t, and we are defining a modulation index m as Vm divided by E by 2. So, that we write this equation here, where m is a factor which is possible to change. Okay. M can change from 0 to 1, okay. And so, the upper and lower voltages from the converter, these two here can be changed. So, it is very easy to understand from waveforms. So, let us see the waveforms. Okay. Now, in this waveform, whatever mathematical analysis we did has been now shown graphically. So, suppose this is the AC voltage which we are trying to produce. Okay. This is the AC voltage, you can see the peak of the AC voltage is Vm, okay, here Vm, the peak of the AC voltage is Vm. On this curve we also are showing the E by 2 and minus E by 2 with respect to this O point here. Here O point is here, E by 2 and minus E by 2, this is the 0 point which has been assumed, okay, E by 2 here and E by 2 down there. Now, if you see the voltage to be produced by the upper arm, because it has to satisfy the Kirchhoff's voltage law. So, what it will do? See, the voltage produced by the upper arm is shown by the red arrows here. The red arrow denotes the instantaneous voltage produced by the upper arm. Okay. Why these red arrows are instantaneous upper arm voltage? Because if you see here, you start from here, you go to E by 2 minus Vu, and of course, neglecting this L di dt. So, E by 2 minus Vu is equal to Vm sin omega t. So, if you go on this waveform, you go from 0, E by 2 minus Vu is what you get Vm sin omega t here. So, this means that this red arrow is indicating the voltage which is produced by the upper arm. Okay. and the magnitude is the instantaneous magnitude is changing with time. Here the arrow length is small, whereas here the arrow lengths are big. Okay. So, big in size here, okay. And this is exactly, or this is consistent with the equations that we had written earlier, but this is just a diagrammatic representation. What about the lower one? What about the lower controllable voltage source, this V L? V L also follows the Kirchhoff's voltage law, and so minus E by 2 plus V L is this L, without this neglecting the L di dt, minus E by 2 plus V L is the V m sin omega t. So, if I go from 0, I go minus E by 2, and then this green arrows, these green arrows indicates the instantaneous magnitude of the lower arm voltage. Okay. It is varying with time, it is minimum here and it is maximum here. Okay. Fine. So, this means that the lower controllable voltage is denoted by the green arrows and the upper controllable voltage is denoted by the red arrows. Now, one thing to note is that the AC output voltage can be changed in magnitude by changing the length of the arrows. So, for example, the AC output can be made like this also. Of course, under that condition, this red arrow here will no longer be of such a length, but will increase up to this point, and similarly the green arrow will be up to this point. Okay. So, therefore, we understand that the magnitude of V m, the magnitude of V m can be changed, and that is exactly what I was talking about the modulation index in the previous slide, that the modulation index is something which is in our hand. Okay. That means, the upper and lower controllable voltage sources can be adjusted in such a way that the AC voltage which is produced at the output of the converter at any point of time can be changed, can be modified. Okay. So, it can be even made 0, you can make the voltage to be 0 also. Now, how much voltage you can produce? The maximum voltage that can be produced from the converter, the maximum voltage that can be produced is this much here. The maximum voltage can be produced like this here. So, this is the maximum voltage, that is the maximum voltage which can be produced, and at that point of time you can see that some of the arrows, a few arrows are almost 0 in magnitude, while some arrows here are getting to the peak, or the length of the arrow is coming up to E. Okay. So, the length of the arrow is E when the maximum voltage is produced and V m is touching this E by 2. Okay. So, when this maximum happens, that is the maximum voltage needed to be produced. Maximum voltage of E needs to be produced from the arm under the condition when V m touches E by 2 here, which I have shown by this curve. There is also one thing to note, and that is all the arrows are unidirectional. So, all the arrows, for example, for the red arrows are all pointing downwards. You can see here all the arrows are pointing downwards, while all the green arrows are pointing upward. Okay. So, the arrows are unidirectional in nature. So, half bridges can be used, because in half bridge we only produce unidirectional voltage. So, we have seen now that the unidirectional voltage with the arms are producing unidirectional voltages, and so half bridges can be used. Now, so far I was talking about MMC being used as a DC to AC converter. So, that is how we have analyzed this waveform. But now it is interesting to observe that if suppose I have an AC to DC application, for example, the MMC is used as a rectifier in an HVDC application, then what do I need to do? In case I have to make or operate this converter as a AC to DC rectifier, then the AC side or the grid is available to me or available to us, and I would like to produce a DC, right. So, therefore, in this waveform this AC voltage is available, it is present as the voltage from the grid, whereas you would like to produce this DC voltage, and during that condition what we have to do? We have to just flip the direction of the arrow. It is very simple, we just flip the arrow direction. So, in this waveform all the arrows are downwards. So, if this arrow waveforms are if the arrow directions are made like this, okay, the opposite part like this, then if this AC voltage is available, then it is possible that the DC voltage will be produced at the output of the converter. So, if we can flip the direction of the arrow, which means the controllable voltage source in the arms, the controllable voltage source in the arms are now commanded to produce a voltage like this here. So, it has now the reference has become opposite. So, since the AC waveform is available here and we are trying to produce a DC, so the arm voltages are now commanded to produce such a voltage. Okay. Again, this is perfectly consistent with the equations of the arm voltages. It is perfectly consistent, you can check it up. So, this Vu it is just that the polarity is reversed, and still, so the advantage is that we are now producing, or we can use this converter as a AC to DC converter, and the same half bridges can be still used, okay, because again the arrows are all unidirectional. Okay. So, the half bridges can be used. So, the same converter, so what I want to say is that by change of the control logic, the same converter can be used for AC to DC conversion or from DC to AC conversion, okay, as we can see from the graph. This is very advantageous, and therefore, for long distance DC transmission, where at the sending end you will convert the AC to DC, and at the receiving end you will convert the DC back to AC, and so both at the sending end and the receiving end we can have the same MMC converter, same MMC. Now, an interesting thing that comes up next is what happens if the DC voltage suddenly becomes lower. Okay. Now, why can or when can this happen? This can happen for a variety of reasons. For example, if the MMC is used as a rectifier and due to some disturbance on the DC side, the DC voltage has been reduced. Okay. Now, if the DC voltage is reduced, we have shown a waveform here. Now, if you observe this waveform here, then you see that now the AC voltage is here and the DC voltage has a magnitude which is lower than the peak AC voltage, right. Now, we observe the arrows. Okay. Now, when the DC voltage is here and more than the AC voltage, then the arrows are downward. Okay. What is this arrow indicating? The arrow indicating the instantaneous arm voltage. The red arrow is indicating the upper arm voltage and the green arrow indicates the instantaneous lower arm voltage. Now, the upper arm during this portion, the arrow direction is downwards, whereas when the AC voltage is more than the DC, then the arrow direction is reversed, and then again here the arrow direction is downward, here the arrow direction is upward. For example, if you observe the red colored waveform, the upper arm voltage. So, therefore, when the DC voltage becomes lesser in magnitude than the AC voltage, then we need bidirectional voltage from the arm. Okay. So, the arm voltage here is bidirectional in nature, sometimes it is positive, sometimes it is negative, right. In this particular waveform, the magnitude of the upward arrow and the magnitude of the downward arrow, they are not same. Okay. But in any case, we see that we need bidirectional voltage from the converter or from the arm of the converter, and so we must use full bridges in these arms, because a full bridge, the difference between a full bridge and a half bridge is half bridge can produce only unidirectional voltage. Okay. So, if there are n half bridges, so 0 Vc, 2 Vc, 3 Vc up to n Vc, that is what the half bridges can produce. But a full bridge can produce plus Vc 0 or minus Vc, that means a bidirectional voltage capability is present in a full bridge. So, if there are n number of such full bridges, it can produce plus n Vc to minus n Vc. So, in this case we see that in this waveform, we see that the bidirectional voltage capability of the arm is needed when the DC bus has a magnitude less than the peak AC voltage. Okay. Again, this is again consistent with the equations that we have derived earlier, VUT and VLT. If you put there, you will see that during this condition VUT has a bidirectional component. Okay. So, it can be plus or means positive as well as negative. Now, what happens if we go on reducing the DC voltage? Okay. This is something very interesting. If you go on decreasing the DC voltage, like you can go up to E equal to 0 or a very small value, it is a possibility. Okay, you go on in decreasing, what happens now? You see that the arrows of course are changing in magnitude. Okay. If you compare this waveform with this waveform, the positive magnitude of the arrow and the negative magnitude of the arrow, they were kind of like different in magnitudes and unequal. Now, when as E becomes closer to 0, then these two magnitudes of the arrows are becoming almost equal, and the converter can actually still work, right. The converter, the arm voltages can still support this condition. Okay. Now, when does this condition happen, that is E becoming 0 or a very small value? When will it happen? It will happen during a short circuit on the DC bus. Okay. Say for example, we have an HVDC line and we have a pole to pole fault, bipolar HVDC line, we have a pole to pole fault. This is a condition where E becomes 0 or a very small value. Okay. So, this is the condition, but during this short circuit fault, when E has become close to 0, then also this converter can support. In fact, the arm voltages during this condition are shown here on this diagram, and you can see that the converter can still work during this short circuit condition, and it is as if during this time the arm voltages are as if you can think of it something like a back EMF. Okay. So, the grid is available, there is a short circuit here, the AC side is available, and the arm voltages are basically are able to sustain this condition by generating an AC voltage here. Okay. And this AC voltage which is being generated by the arm is kind of like a back EMF to the AC grid, and it prevents the very high rate of rise of current during this short circuit condition. So, the arm voltages here, you can see the arm voltages, you can command the arm voltages to produce a voltage here at this point, which is directly opposing this AC voltage, which can pump in energy into the short circuit condition, and during this time the waveforms can be made like this here, which it has been shown. Of course, so therefore, so what is the advantage? The advantage is the short circuit current, because this is a very severe fault, you have a pole to pole fault, but the short circuit condition can be tolerated at least for certain duration of time. Okay. But we will of course need the full bridge, definitely we will need the full bridge converter in order to have something like this. Okay. But of course, this condition cannot be sustained for a long time, definitely it cannot be sustained, because remember that the cells have capacitor. Okay. So, there is some stored energy in the capacitor, and if we have to operate the converter during this time, what we are utilizing basically is the stored energy of the capacitors in the cells, which are helpful in creating this back EMF, and this energy will quickly dry down, it will quickly get exhausted, and then we have to immediately shut down the converter. But at least for the time when this short circuit happened and the time for which the AC side breaker opens, during this time, say about 3-4 cycles, 80 to 100 milliseconds, during this time when the circuit breaker has not opened on the AC side, during this time it is possible for the converter to kind of like prevent a very high rate of rise of current during a short circuit condition. So, such a condition is shown in this graph here.